So the paper that we all read before class discusses how some concurrent applications access a database. So before we get into the results of the paper, it's good to have some background about what concurrency guarantees modern databases actually offer us and what it costs us to use them. So here's just an overview of some database systems. The first row is showing relational databases and what concurrency features they have, and these are just taken for this case specifically from Postgres. So it offers transactions, locks, and for your transactions you can execute them at multiple isolation levels. So this provides some flexibility, and we'll get into a little bit more details about what those isolation levels actually mean later. Another database system is MongoDB, which is a document store. So that provides atomic updates at the document level, but once you get into operations on multiple values, it drops down to a weaker guarantee, which would be multi-version concurrency control. So we talked about that before in the NoSQL lecture, but just a refresher. So when you start an operation and you need a data value, you'll just end up reading whatever data value is available at that server that has the most recent timestamp. And after your operation is finished, you'll write a new version of that data which gets a new timestamp. So this isn't the strongest possible guarantee because there could be some discrepancy about what exactly is the latest piece of data. So the data you get depends on what server you're executing your operation on, as well as what other operations are going on concurrently. So it's eventual consistency in that eventually all servers will agree on what the latest timestamp is for a particular piece of data, but that actually requires updates to stop and all the servers to communicate. So not the strongest possible guarantee. So some other things to look at are graph databases. So Neo4j also supports transactions and locks, but up until 2015 it actually executed all those transactions sequentially, so there was no issues in concurrent access. And then another NoSQL database type is key value stores. So Redis is one example of that, and it also has transactions and locks, but it executes those transactions serially, and that turns out to be fine for Redis since all the operations are so simple. You're just looking at particular keys. Doing it sequentially turns out to be fine for performance. So for relational databases, I said there was those different isolation levels. So here's just an overview of some possible isolation levels. So starting at the weaker end, there's read committed, which that just means if you're running a transaction, that transaction will not see writes from other transactions unless those transactions have already committed. So that's definitely something that you want. Another isolation level is repeatable read. So what this says is if you're running a transaction and you end up reading a data value, you'll never see in that transaction that data value change unless it was because your transaction updated. So there won't be, you won't see the effects of some concurrently executing transaction overwriting a value that you've already read in your transaction. So that's another nice thing that you would want, but it's not everything. So there's also a stronger isolation level, which will be snapshot isolation, and this has your transaction behave as if it took a snapshot of the data, essentially freezing the database when it starts the transaction, and it will only successfully finish the transaction if there were no conflicting writes to any of the data values that your transaction wrote. So that's pretty good, and it's good enough for a lot of cases. But then the strongest possible guarantee you could get serializable isolation, and so that has your transactions behave as if they actually executed one after the other. So transaction 1 starts, transaction 1 finishes before some other transaction 2 could start. So the different isolation levels have performance costs. The paper we read says, given serializability's performance and availability overheads, developers at scale have largely eschewed the use of serializable transactions. And then it says that 75% of the things that they looked at actually didn't require serializable. So if you look at this table on the right, it's just showing the default isolation level of a bunch of relational databases, and then the right column is the maximum possible isolation level that supports. Taking a look at a specific row, there's MySQL, which defaults to repeatable read, which is one of those weaker isolation levels, and it defaults to it because it gives good performance. But if you really need serializable isolation, MySQL has that available, but you have to opt in. So taking a look specifically at what the issues can be with a weak isolation level, there's this thing called lost update, and essentially it's when you have two transactions executing simultaneously and it looks like one of the transactions didn't get to execute its write. So in this example there's T1 and T2, and let's assume that this value that they're both reading X starts at 0. So you would hope that T1, when it reads X, sees 0, then it writes the value X plus 2 to X, so X should end up with value 2. And then transaction 2 does a similar thing where it reads X and it increments it by 1. So if they both execute sequentially, you would see X get incremented by 2 and then by 1, and you would see the final value being 3. But suppose that both transactions start, they both read X, they both see 0, and then transaction 1 finishes and writes the value 2, and then transaction 2 finishes and writes the value 1. The final value for X is 1, even though both transactions executed. So we wanted to see 3 at the end, but we saw 1, and it's because transaction 1's update got lost. And a generalization of that is write skew. So this is, instead of just looking at one variable X that's in our database, we'll look at two different variables X and Y. So in this case, transaction 1 and 2 are providing dependency between variables X and Y. So transaction 1 is saying read X, if it's 0, write 1 to Y, and then transaction 2 does the opposite, read Y, if it was 0, then write 1 to X. So if these transactions have to execute at serializable isolation, at the end of the day, if they both start at 0, we can only see either X or Y end up with 1. But if they both start out and they both read 0s, they'll both write 1s. So that's write skew. And snapshot isolation, which we looked at before, only prevents lost updates, since that's only looking at a single data value X. But once you look at more than one data value, snapshot isolation doesn't give you the same result as serializable isolation. So we looked at this other paper which examined the concept of highly available transactions, and what it did was it looked at this existing theorem, the CAP theorem, which says that you can have at most 2 of consistency, availability, and partition tolerance in your database system. And so essentially it's saying that you can't have performance and strong concurrency guarantees. But what the paper points out is that the theorem only applies specifically to a consistency model called linearizability. But if you're willing to give up the strong guarantee of linearizability, you can actually get a database system which gets all 3 of the CAP elements, and they're going to call that highly available transactions. So essentially, the paper shows that if you want one of the really strong guarantees like snapshot isolation, you can't get all 3 of these things, but if you're willing to go for a weaker isolation level, you can actually get good performance. So here's just some graphs from the paper. The interesting things to look at here are the red asterisk is for an eventual consistency model, and the blue box is for single key linearizability. If you take a look at the 2 graphs on the left, that's for their benchmark running all in the same AWS region, so there's minimal network costs. And in that case, if you look at the top graph, when you require single key linearizability, you get about your latency is about twice as long as if you only required eventual consistency. And then if you look at the bottom graph on the left, it shows that the throughput for linearizability is about half. And then if you take a look at the two graphs on the right, that's where their benchmark is running now across multiple AWS regions, and things get a little worse for the strong guarantee. Your throughput is now, in the worst case, only 1/40th of what you could have gotten with eventual consistency, and then your latency can be 10 times as much.